Okay, so this is our example I wanted to look at. Um, this is similar. This is a similar type of idea to Calvin and his record player, but a little different. So 2 points on the same circle, or two circles that share a hub, they're fixed together for whatever reason. They have the same angular speed, but their linear speed is going to be different. This is a different case where we've got two circles that have their own hubs, meaning they can have different speeds that they turn at, different angular speeds, but they're connected by a chain or a rope. So these are my terrible gears. They look really bad, but these are supposed to be gears here. Like in a bike, you have some big gears back here, some little gears up here, or vice versa. So we've got this problem here. We want to talk about how these different linear and angular speeds relate to each other. So in this example, I've got my rear gear here has a radius of 15 centimeters. My forward gear has a radius of 8 centimeters. And they tell us a little bit of information. They tell us that this rear is rotating at 25 rotations in 36 seconds. I don't know why someone would measure it that way. I don't know how they decided to do that. But somehow we've been given this number by a customer or whatever, and we have to figure out some angular speeds for that customer. I don't know. I'm trying to think of a great situation where this would be feasible. But changing between these two things shouldn't be difficult. So first off, the relationship between the rotations and the amount of time, from that we can come up with that angular speed. So the question actually asked me, find the angular speed of each of these two gears. So what is my first one? I've labeled it omega 1 for the first one. Well, that's just the angle I've gone through in a given amount of time. I've gone through 25 rotations. Each rotation is 2 pi. So I've gone through, let me change color here. I've gone through 25 times 2 pi radians. Right? Each rotation is 2 pi radians. I've gone through 25 rotations, and that took me 36 seconds. So I can simplify that. I could cancel out a 2 from each of these. 2 and 36. That leaves me with, on the top I've got 25 pi radians. On the bottom I've got 36 divided by 2 is 15, 16, 17, 18 per 18 seconds. Or you could say I've got 25 pi over 18 radians per second. So I've got the first part figured out. The question is, how can I relate that to this second angular speed? The way I'm going to do that is using my relationship. I know that these two things have to have the same linear speed. I found the angular speed of that one. From that I can figure out the linear speed using my rule here. So using that, I can now find my linear speed. So R is, in our case, 15. The case of my first circle there. 15 times 25 pi over 18 rad per second. Okay? And gosh, I could simplify that. I'm just going to multiply that out and leave it as a gross unsimplified fraction. So 15 times 25 is 375. Okay, and now I've got a unit there. My radius was in centimeters. Since radians are not really a unit, I don't just ignore those now. So now I've got this thing in centimeters per second. So now I've got my linear velocity of this thing. So I've got the angular velocity, I've got the linear velocity, but that's the key idea here, is that this has this linear velocity, this has this linear velocity. Those two have to be the same, because whatever point I've got fixed here, moving at this speed, has to be moving along this one at the same rate. Right? They're physically connected along the outside of the circle rather than along that center. So the speed along the outside is the one that's connected, not the speed of the interior angle there.